Hello everyone, welcome to our channel. In today's video, we are diving into the world of object-oriented programming or OOP in Python. Whether you're preparing for a job interview or just looking to brush up on your OOP concepts, we've compiled a list of the top 50 questions that you're likely to encounter. From the fundamentals of classes and objects to more advanced topics like inheritance and polymorphism, these questions will help you solidify your understanding and prepare you for your next coding interview. So grab a notebook and let's get started. Question 1: what is object-oriented programming in Python? Object-oriented programming in Python is a paradigm that structures code around objects which are instances of classes. This approach allows developers to organize and model their programs by grouping related data and functionalities within a defined blueprint called a class. Classes act as templates for creating objects that share common attributes and behaviors. OOP enhances code readability, promotes modularity, and encourages reuse through four primary principles: encapsulation, inheritance, polymorphism, and abstraction. Encapsulation is the technique of bundling data attributes and methods functions within a single unit, such as a class, restricting direct access to some components. This enables secure and organized data management as only specific methods expose or modify data, making the code more reliable and easier to maintain. Inheritance is a mechanism that allows new classes to derive or extend features from existing ones, promoting code reuse and establishing a relationship hierarchy between classes. For example, a car class can inherit properties from a vehicle class, gaining access to its attributes and methods without rewriting them. Polymorphism allows for flexibility in coding, as it lets functions or methods operate on different data types or objects without modifying the code. This is achieved through method overriding, where derived classes modify inherited methods to provide specialized functionality. Finally, abstraction simplifies complexity by exposing only essential parts of an object to the user while concealing internal details. This means users interact with a clear and simple interface without needing to understand the underlying implementation. By organizing code with these principles, OOP helps create modular, scalable, and reusable applications, making it ideal for projects that require efficient and structured code. Practical example, like the person class example demonstrates the foundational concepts of object-oriented programming by encapsulating the data and behavior associated with the person. The class itself acts as a blueprint, defining attributes and methods shared by all instances or objects of this class. When defining the person class, two primary attributes, name and age, are included to represent the characteristics of each person. The underscore underscore init method, known as the constructor, is a special method that initializes these attributes when a new person object is created. This method assigns values to self.name and self.age, where self refers to the specific instance being created, ensuring each object has its unique name and age. The display underscore info method within the person class is a behavior that prints the object's name and age attributes in a formatted string. By calling this method, each person object can display its information. Creating objects like person1 and person2 involves calling the person class and passing the required arguments name and age. Each object thus represents an individual person with their specific details. Calling display underscore info on person1 outputs name Alice, age 30 displaying Alice's data, while calling it on person2 prints name Bob, age 25 showcasing Bob's information. This simple example illustrates how classes bundle attributes and methods, creating organized, reusable structures in code. Question 2: explain the four main principles of OOP encapsulation: inheritance, polymorphism, and abstraction. Encapsulation is a core principle that involves combining data attributes and functions methods within a single unit, known as a class, and restricting access to specific components. By controlling access to the internal state of an object, encapsulation helps maintain data integrity and security. This is achieved by defining public methods, often referred to as getters, and setters that allow controlled access to the object's attributes. Encapsulation ensures that only trusted parts of the code can modify the internal data, preventing unintended or harmful interactions. It ultimately allows a clear separation of the object's inner workings from its interface, making the code easier to manage and understand. Inheritance is the principle of creating new classes or subclasses based on existing ones called superclasses. This feature enables a subclass to inherit attributes and methods from its superclass, promoting code reusability and reducing redundancy. For instance, if a superclass named vehicle defines common attributes like speed and color, subclasses like car and bike can inherit these properties without redefining them. This establishes a hierarchical relationship where subclasses can further extend or override the inherited functionalities to add or modify features as needed. Inheritance enables the development of complex systems by building on existing tested code structures, enhancing scalability and maintainability. Polymorphism is the concept that allows objects of different classes to be treated as instances of a common superclass, providing flexibility and generalization. With polymorphism, a single method can behave differently based on the object calling it. For example, a method called make underscore sound could be defined in a superclass called animal, while each subclass, such as dog or cat, implements its version of make underscore sound. When called on an instance, the appropriate subclass's version of make underscore sound executes, allowing the code to handle different objects seamlessly through a unified interface. This capability to adapt based on context makes polymorphism particularly powerful for designing adaptable, extensible code. Abstraction involves concealing complex implementation details and exposing only the essential aspects of an object to the user, reducing the complexity of interactions. By showing only the relevant details, abstraction allows users to interact with objects without needing to understand how they function internally. For example, a database connection class might allow the user to connect, disconnect, or run queries on a database without knowing the underlying network protocols or data handling procedures. Abstraction streamlines code by emphasizing what objects do over how they do it, resulting in a clean and user friendly interface that simplifies coding and minimizes potential errors. Question 3: what is a class in Python and how do you define it? A class in Python serves as a blueprint for creating objects, enabling a structured approach to building programs by grouping related data and behaviors into a single unit. When you define a class, you specify a set of attributes, data, and methods functions that each instance or object created from the class will inherit. This way, classes provide a foundation for organizing code and creating multiple instances with a consistent structure and behavior, promoting modularity and reuse. Defining a class in Python is simple and starts with the class keyword followed by the class name and a colon. Inside the class, the underscore underscore init method is often defined as the constructor, which initializes attributes for each object created. Methods, which represent behaviors, can then be added to perform actions using the object's data. By using classes, Python allows developers to model real-world entities and manage complex code bases more efficiently, as all objects created from a class share the same characteristics and functionalities defined in the blueprint, making the code more modular, organized, and scalable. Practical example. The car class example showcases the basics of object-oriented programming by encapsulating the attributes and behavior associated with the car. Here, the car class serves as a blueprint for creating car objects with specific properties and functions. The class includes two main attributes, make and model, which represent the manufacturer and model of each car. These attributes are initialized in the underscore underscore init method, a special constructor method that sets up each instance when it is created. The self keyword refers to the specific instance, ensuring that each car object holds its unique make and model values. In addition to attributes, the car class also includes a method display underscore info which provides the behavior associated with the class. This method is responsible for displaying the car's make and model in a formatted string. When called, it prints the information for each specific car object. For instance, creating two objects, car 1 and car 2, allows us to represent two distinct cars, one a Toyota Camry and the other Honda Civic. By calling display underscore info on each object, we see the unique information displayed car make Toyota, model Camry for car 1 and car make Honda, model Civic for car 2. This example illustrates how classes help organize code, allowing each object to store and display specific data while sharing a common structure and functionality defined in the class blueprint. Question 4. How do you create an object from a class? In Python, an object is an instance of a class created to represent a specific entity with the attributes and behaviors defined in the class blueprint. To create an object, you simply call the class name followed by parenthesis, which triggers the class's underscore init method. This method acts as a constructor, initializing the attributes with the values provided and setting up the new instance with all the characteristics specified in the class. For example, if we have a person class with name and age attributes, calling person Alice 30 will create an object that stores the information for Alice as a person with age 30. When a class is called to create an object, Python automatically invokes the underscore underscore init method, passing in any arguments necessary for initializing the instance's data. Inside this method, the self keyword represents the current instance, allowing each object to maintain its unique values while sharing the same structure. This process enables you to create multiple objects from a single class definition, each with its specific data. By creating objects from classes, Python allows you to model real-world entities and manage data more effectively within a structured, reusable framework. Practical example. In this example, the person class is defined as a blueprint for creating objects that represent individual people, each with specific characteristics such as name and age. The class includes an underscore underscore init method, which serves as the constructor responsible for initializing these attributes when a new person object is created. When an instance of person is created, the underscore underscore init method receives values for name and age, assigning them to self.name and self.age. This ensures that each object created from the person class has its unique values for name and age. In this code, two objects, person1 and person2, are created by calling the person class with specific attribute values. Person1 is initialized with name as Alice and age as 30, while person2 is initialized with name as Bob and age as 25. These objects represent separate individuals, each with distinct values for the name and age attributes. We can then access and print these attributes using dot notation, such as person1.name and person2.age, which outputs Alice 30 for person1 and Bob 25 for person2. This demonstrates how objects created from a class share a common structure but hold individual data, allowing for organized and flexible data representation. Question 5. Explain the underscore underscore init method and its purpose. The underscore underscore init method in Python is a special method known as a constructor, which automatically runs whenever a new object is created from a class. This method is essential for initializing the object's attributes with specific values provided at the time of creation. By setting up the initial state of the object, The underscore underscore init method ensures that each instance of a class is created with the necessary data and is ready for use. When a class is called to create a new object, Python invokes the underscore 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 init method and passes any arguments given during object creation. Within this method, the self keyword represents the current instance, allowing each attribute to be tied specifically to that object. For example, in a person class, the underscore underscore init method might accept arguments for name and age and assign these values to self.name and self.age. This way, every person object can store unique information relevant to each individual, even though all objects share the same class structure. The underscore underscore init method simplifies the process of creating objects with predefined attributes and ensures that each instance is properly configured upon creation. Practical example. In this example, the book class is defined to represent books with specific attributes, including title, author, and pages. The underscore underscore init method, also known as the constructor, is used to initialize these attributes each time a new book object is created. When an instance of book is instantiated, the underscore underscore init method assigns the values provided for title, author, and pages to the object's respective attributes, creating an organized structure to store book details. Here, two objects, book 1 and book 2, are created by calling the book class with specific arguments. Book 1 is initialized with the title To Kill a Mockingbird, the author Harper Lee, and a page count of 281, while book 2 is initialized with the title 1984, the author George Orwell, and 328 pages. Each object thus represents a unique book with its specific details stored in the class attributes. By accessing these attributes using dot notation such as book1.title and book2.pages, we can retrieve and display each book's information. Printing book 1 outputs To Kill a Mockingbird Harper Lee 281 pages, and printing book 2 shows 1984 George Orwell 328 pages. This demonstrates how the underscore underscore init method efficiently sets up each object with relevant data upon creation, providing an organized, reusable way to handle information about different books within a consistent structure. Question 6. What is the difference between a class and an instance? Definition: a class is a template that defines attributes and methods for objects. It provides a blueprint for creating objects but does not hold specific data itself. An instance, on the other hand, is a unique object created from a class. Each instance represents a specific object with its actual data, created by following the structure defined by the class. For example, person could be a class, while person 1 and person 2 are instances of that class, each representing individual persons. Data storage classes do not store data until instances are created. They merely define what data attributes and methods will be available for each instance. When an instance is created, it stores actual data in the attributes defined by the class. For instance, while the person class defines the attributes name and age, these attributes only hold specific values like Alice and 30 in the person 1 instance. Example classes serve as a general definition or structure, such as person defining what each person's data and actions will be. Instances are individual representations created from that class. If person 1 is an instance of person, it could represent Alice, 30 years old, while person 2 might represent Bob, 25 years old. Each instance has its unique data, even though they share the same structure defined by the class. Attributes and methods classes define attributes and methods for instances to use, setting up a framework that each instance will follow. However, each instance has its own copy of the attributes and can call the methods independently. For example, a person class may define an attribute name and a method introduce, allowing each instance like person 1 and person 2 to store unique names and independently use the introduce method to display their specific information. Practical example. Where in this example, the person class is defined to create objects or instances representing individual people, each with specific attributes like name and age. The underscore underscore init method is used as a constructor to initialize these attributes whenever a new person object is created. By defining self.name and self.age within this method, each instance of the person class can store unique values, allowing us to create multiple instances with distinct characteristics. When we create person 1 and person 2, we pass in specific data for each. Person 1 is initialized with the name Alice and age 30, while person 2 is initialized with the name Bob and age 25. Each object holds its own data in the attributes name and age thanks to the initialization process in the underscore underscore init method. Accessing the data stored in these instances involves dot notation, where we specify the instance and the attribute name. Calling person1.name and person1.age retrieves Alice and 30, while person2.name and person2.age retrieves Bob and 25. This approach highlights how classes provide a general structure while allowing each instance to hold unique data, making it possible to create organized and reusable code for managing multiple individual objects. Question 7. How does encapsulation work in Python? In Python, encapsulation is a core principle of object-oriented programming that combines related data attributes and methods functions within a single class, allowing for better organization and control. By encapsulating data and behavior within a class, we create a structured unit that groups related functionalities and data together, making the code more modular and manageable. Encapsulation not only organizes code but also provides a protective barrier around the internal state of an object, helping prevent unintended or harmful modifications. Python allows us to control access to data and methods by using different types of attribute visibility. Attributes intended for public access are defined with no special syntax, while attributes intended to be private are often prefixed with an underscore egg underscore attribute. Although Python does not enforce strict access control, prefixing attributes with an underscore signals to other developers that these elements are intended for internal use only. For more controlled access, we can define getter and setter, methods that allow data to be read or modified in a controlled way, ensuring data integrity and secure access. This encapsulation approach allows objects to maintain a consistent, safe state while exposing only the parts necessary for other code to interact with, making the code more robust and easier to debug. Encapsulation in Python. In Python, encapsulation allows for different levels of attribute visibility, which helps to control access to data stored within an object. Public attributes are the default type and can be accessed directly from outside the class without any restrictions. These attributes do not have any underscores in their names, and they are openly available for reading and modifying, making them suitable for data that should be accessible without any protective measures. Protected attributes are those prefixed with the single underscore eg underscore attribute. Although they can still be accessed from outside the class, the underscore signals that these attributes are intended for internal use only and are not meant to be modified or accessed directly by code outside the class. The single underscore is more of a convention than a strict rule in Python, serving as a reminder to developers that these attributes are protected and should be accessed with caution to maintain code integrity. Private attributes are prefixed with double underscores e.g. underscore underscore attribute, making them strictly internal to the class. Python achieves this restriction through a process called name mangling, which alters the attribute's name in a way that prevents direct access from outside the class. By renaming the attribute in the background, Python makes it harder to accidentally or intentionally modify private data adding a layer of protection that keeps critical data safe from external influence. To provide controlled access to private attributes, Python uses getter and setter methods. These methods act as intermediaries that allow reading and modifying private attributes without exposing them directly. Getters retrieve the attribute's value while setters modify it, both under controlled conditions. This approach ensures that private data remains protected while still enabling flexible access through these controlled pathways. By combining public, protected, and private attributes with getters and setters, Python provides a flexible and secure way to manage data encapsulation, enhancing the reliability and maintainability of code. Practical example. In this example, the bank account class demonstrates encapsulation in Python by defining attributes with varying levels of access control: public, protected, and private. The account underscore holder attribute is public, meaning it can be accessed directly from outside the class without restrictions. In this case, account underscore holder holds the name of the account owner, and accessing it directly through account.account underscore holder returns Alice as expected. The underscore account underscore type attribute is protected, indicated by the single underscore prefix. Although it is accessible from outside the class, the underscore signals that it is intended for internal use only and should not be modified directly. Here, underscore account underscore type is set to savings, which is displayed when accessed via account underscore type, reminding developers that direct access to protected attributes should be handled cautiously. The underscore underscore balance attribute is private, marked by a double underscore prefix to restrict direct access from outside the class. This attribute holds the account's balance and is hidden from external access through name mangling, preventing accidental modifications to this sensitive information. To access the private underscore underscore balance attribute, the class includes a getter method, get underscore balance, which safely retrieves the balance amount. This controlled access ensures that the internal balance remains protected while still accessible in a secure way. The bank account class also includes a setter method, deposit, which allows controlled modification of the private underscore underscore balance attribute. The deposit method checks if the deposit amount is positive, adds it to the balance, and prints a confirmation message. This controlled approach prevents invalid modifications and ensures that updates to the balance follow specific rules. For example, calling account.deposit 500 increases the balance by 500 and displays deposited 500. By calling account.get underscore balance, the updated balance is shown as 1500. This example illustrates how encapsulation in Python combines public, protected, and private attributes with getter and setter methods to safeguard data and enforce safe interactions with the objects in its internal state. Question 8: explain public, protected, and private attributes in Python classes. In Python, attributes in a class can be defined with varying access levels to control how and where they are accessed, which improves data security and clarity in code. These access levels include public, protected, and private attributes, each serving a specific purpose in how they guide the usage and modification of data within a class. Access levels in Python classes. In Python, access levels in classes help control how attributes can be accessed and modified, making it easier to manage data security and integrity. Python defines three primary access levels: public, protected, and private, each with specific characteristics and recommended use cases. Public attributes are the most accessible, defined without any underscores. Public attributes can be accessed from anywhere, both within the class and from external code, making them suitable for data that does not require protection. By default, attributes in Python are public if they are defined without underscores. For instance, self.name in a class would be a public attribute, allowing direct access and modification from outside the class. Public attributes are useful for data that does not impact the class's internal integrity or security, and they promote open interaction when restrictions are unnecessary. Protected attributes are prefixed with a single underscore e.g. underscore attribute. While Python allows access to protected attributes from outside the class, the single underscore signals to developers that these attributes are intended for internal use within the class and its subclasses. This access level provides a gentle warning that these attributes are not meant for unrestricted external modification and should be handled with care. For example, self dot underscore balance could be a protected attribute in a class, indicating that while the balance can be accessed directly, if necessary, it is better managed within the class or its subclasses. Protected attributes are often used when we want to provide limited access but do not require strict enforcement, typically in cases where subclasses need direct access. Private attributes are defined with a double underscore prefix e.g. underscore attribute, making them inaccessible from outside the class due to Python's name handling process. This process modifies the attribute name in a way that prevents direct access from external code, effectively restricting it to the class where it was defined. Private attributes are ideal for sensitive data that should not be exposed or modified directly, as they help protect the internal state of the object. For instance, self.__password would be a private attribute, meaning that it is only accessible through specific methods such as getters and setters that control how it is accessed and modified. Private attributes are essential for securing data that could affect the object's stability or security if accessed inappropriately. By using these access levels, public, protected, and private, Python provides a flexible yet organized way to manage data accessibility in classes, making it easier to indicate intended usage while protecting the object's integrity. Question 9: what is inheritance and why is it used? Inheritance is a key concept in object-oriented programming that allows one class called the subclass to inherit attributes and methods from another class known as the superclass. This enables code reuse, as the subclass can use or extend the functionality of the superclass without redefining it. For example, a vehicle class with shared attributes and methods can be inherited by subclasses like car and bike, which add their unique properties. Inheritance promotes logical organization by establishing a class hierarchy, grouping related classes, and reducing redundancy. This approach improves code readability and maintenance, making it easier to manage shared functionality and create structured, scalable programs. Practical example. In this example, we define an animal class as the parent or superclass to represent a general concept of an animal. The animal class has an underscore init method, which initializes the species attribute for any animal object created from this class. Additionally, the class includes a make underscore sound method that outputs a general message. This animal makes a sound when called, indicating that all animals have the ability to make sounds. The dog class is then defined as a child or subclass that inherits from animal, meaning it automatically gains access to the attributes and methods defined in the animal class. In the dog classes underscore init method, we use super dot underscore init species to call the animal class's constructor and initialize the species attribute. This allows us to set both the species and breed attributes when creating a dog object, with breed being specific to dog and not found in the general animal class. In the dog class, we also override the make underscore sound method to give it a more specific behavior, as dogs have a unique sound. Instead of the generic message, calling make underscore sound on a dog instance outputs woof. Woof to reflect a dog's bark. This method override shows how inheritance allows subclasses to customize or extend the behavior of the superclass. When we create an instance of animal as generic underscore animal and call make underscore sound, it outputs the generic message. But calling make underscore sound on an instance of dog outputs woof. Wolf illustrating how the dog subclass can tailor the functionality it inherits from animal to better fit its specific characteristics. Question 10 explains single inheritance with an example. Single inheritance is when a subclass inherits from a single parent class, allowing it to access and extend that class's properties and behaviors. This approach is ideal for creating a specific version of a general class without the need for additional parent classes, keeping relationships clear and maintainable. For example, a vehicle class might define general attributes like speed and methods such as start and stop. A car subclass could inherit from vehicle, gaining these features while adding its own, like number underscore of underscore doors or a honk method. Single inheritance is useful when a specialized class only requires one primary parent, making code reuse straightforward and organized. Practical example. In this example, we define a vehicle class as a parent class that represents general characteristics of a vehicle, such as brand and max underscore speed. The vehicle class includes an underscore underscore init method that initializes these attributes and a display underscore info method to print out the brand and maximum speed. This class serves as a general template for vehicles, providing a base structure that other, more specific classes can build upon. The car class is a child class that inherits from vehicle, demonstrating single inheritance. By inheriting from vehicle, the car class gains access to all of vehicle's attributes and methods, such as brand, max underscore speed, and display underscore info. The car class has its own underscore underscore init method, which calls the parent class's constructor using super dot underscore underscore init brand, max underscore speed to initialize the inherited attributes. In addition, it defines a new attribute, fuel underscore type, specific to cars, and an extra method, display underscore car underscore info, that displays information about the car's fuel type. When an instance of the car class, my underscore car, is created with the brand Toyota, a maximum speed of 180 km/h, and the fuel type petrol, it combines attributes from both the vehicle and car classes. Calling my underscore car dot display underscore car underscore info first uses the inherited display underscore info method from vehicle to print the brand and max speed, then displays the car specific fuel type. This example shows how single inheritance allows car to reuse and extend vehicle's functionality, creating a clear and organized structure. Question 11. What is multiple inheritance? Give an example. Multiple inheritance is a feature in object-oriented programming that allows a single class, known as the child class, to inherit attributes and methods from more than one parent class. This means the child class can combine functionalities from multiple sources, making it more versatile and capable of performing a range of tasks without redefining shared features. Multiple inheritance can be especially useful when a class needs to inherit behaviors from two or more distinct categories. For example, a class flying car might inherit from both a vehicle class and an aircraft class, combining the properties and methods associated with both ground and air vehicles. However, multiple inheritance requires careful management, as inheriting from multiple parent classes can lead to conflicts, especially if the parent classes have methods or attributes with the same names. Python handles these conflicts through a method resolution order, MROW, which determines the sequence in which classes are checked when accessing a method or attribute. This order helps ensure that the correct version of a method or attribute is accessed, reducing the risk of unexpected behavior. While powerful, multiple inheritance should be used with consideration to avoid unnecessary complexity, ensuring that the child class inherits from only relevant and complementary parent classes. Practical example. In this example, multiple inheritance is demonstrated by creating a duck class that inherits from two parent classes, flyer and swimmer. Each parent class represents a specific ability. The flyer class defines a fly method, which prints the message this animal can fly, symbolizing the ability to fly. Similarly, the swimmer class includes a swim method that outputs this animal can swim, representing swimming capability. Each of these classes encapsulates a single skill, allowing any class that inherits from them to gain these abilities. The duck class inherits from both flyer and swimmer using multiple inheritance to combine flying and swimming functionalities. This approach reflects the real life characteristics of a duck, which can both swim and fly. In addition to the inherited methods, the duck class defines its unique quack method, which prints quack when called. This makes the duck class versatile as it combines attributes from both parent classes with its unique behaviors. When an instance of duck is created named duck, it has access to methods from both the flyer and swimmer classes as well as its own. Calling duck.fly invokes the fly method from flyer, outputting this animal can fly. Similarly, calling duck.swim accesses the swim method from swimmer, printing this animal can swim finally. Calling duck.quack displays quack. Quack using the duck class's unique method. This example illustrates how multiple inheritance enables a class to inherit features from multiple sources, creating a more flexible and multifunctional class while reflecting real-world characteristics. Question 12. What is the superfunction and why is it used? The superfunction in Python is a built-in tool that allows a child class to call methods or access properties of its parent class. It returns a temporary object representing the parent class, enabling the child class to extend or reuse inherited functionality without directly referencing the parent class name. Using super enhances code readability and adaptability, especially in inheritance structures. For example, in a child classes underscore underscore init method, super dot underscore underscore init can be used to run the parent class's initializer, allowing the child class to build on the parent setup. This promotes code reuse and simplifies modifications in class hierarchies. Practical example. Example. In this example, we define an animal class as the parent class, which represents general characteristics of animals. The animal class includes an underscore underscore init method to initialize the species attribute and a make underscore sound method that prints the message this animal makes a sound. This method provides a generic behavior representing that all animals can make sounds but without specifying any particular type. The dog class is defined as a child class that inherits from animal, demonstrating inheritance and the use of the superfunction. In the dog classes underscore underscore undid method, super dot underscore underscore init species is called to invoke the parent classes underscore underscore undid method, initializing the species attribute in animal while also allowing the dog class to add its unique breed attribute. This use of super ensures that the shared species attribute is correctly initialized without duplicating code from the parent class. The dog class also overrides the make underscore sound method to customize it for dogs. By calling super.make underscore sound, it first invokes the parent class's version of make underscore sound, which prints the general message this animal makes a sound. It then adds a specific behavior for the dog class by printing woof. Woof to represent a dog's bark. This combined approach allows dog to expand on the functionality of animal while retaining the parent's general behavior. When an instance of dog is created, such as dog dog canine, Labrador, it has access to both the species and breed attributes. Calling dog.make underscore sound first prints the general message from animal and then the dog specific message resulting in this animal makes a sound. Woof. Woof. This example demonstrates how super facilitates code reuse and extension in inheritance, allowing the child class to build on modify parent functionality as needed. Question 13. How does method overriding work in Python? Method overriding in Python allows a subclass to replace a method defined in its superclass with its own version. When a subclass defines a method with the same name and parameters as the superclass method, the subclass's version overrides it. This means that calling the method on an instance of the subclass will execute the subclass's version, providing specific functionality unique to that class. For example, if an animal class has a make underscore sound method that prints this animal makes a sound, a dog subclass can override this method to print woof. Woof instead. This lets subclasses refine or customize inherited behavior without changing the superclass. Additionally, subclasses can still access the superclass's method using super, enabling them to extend functionality rather than replace it entirely. Practical example. E- In this example, we define an animal class as a parent class with a make underscore sound method that prints a generic message. This animal makes a sound. This method provides a general behavior, representing the idea that all animals can make sounds without specifying any particular type of sound. The dog class is defined as a subclass that inherits from animal and overrides the make underscore sound method. Instead of using the generic message from animal, the dog class provides a specific behavior by redefining make underscore sound to print woof. Woof. This customization reflects a dog's unique sound, making dog more specialized than its parent class. When instances of both animal and dog are created, each class's make underscore sound method behaves according to its definition. Calling make underscore sound on an instance of animal, such as generic underscore animal, prints this animal makes a sound. In contrast, calling make underscore sound on an instance of dog, such as dog prints wolf. Wolf, this example illustrates method overriding, where the subclass dog replaces the parent class's method with its own version, allowing it to provide specific functionality unique to its purpose. Question 14. What is polymorphism in Python? Polymorphism in Python is an OOP concept that allows objects of different classes to be treated as instances of a common superclass, enabling a consistent interface across multiple types. It allows methods with the same name to behave differently depending on the object calling them, enhancing flexibility and code reusability. For example, if both dog and cat classes have a make underscore sound method, calling make underscore sound on a dog instance might print woof. Woof, while on a cat instance it might print meow. Polymorphism allows such varied behaviors under a shared method name, simplifying how functions handle diverse object types and making code more adaptable and scalable. Practical example. In this example, we demonstrate polymorphism in Python by defining an animal parent class with the make underscore sound method that outputs a general message. This animal makes a sound. This method represents the idea that all animals have the ability to make sounds without specifying any particular sound. We then define two subclasses, dog and cat, which inherit from animal and each override the make underscore sound method to provide specific sounds. The dog class's make underscore sound method prints woof. Woof, while the cat class's make underscore sound method prints meow. These overrides allow each subclass to offer behavior unique to its type while still following the same interface set by the animal class. To demonstrate polymorphism, we create a list animals containing instances of dog, cat, and animal. By iterating over this list and calling make underscore sound on each object, Python dynamically determines which make underscore sound method to execute based on the object type. This results in woof. Woof for the dog instance, meow for the cat instance, and the generic this animal makes a sound for the animal instance. This example illustrates polymorphism, where the same method called make underscore sound produces different outputs based on the object type. This ability to treat different classes through a common interface simplifies code and enhances flexibility, allowing varied behaviors under a shared method structure. Question 15, explain method overloading and whether it's supported in Python. Method overloading allows multiple methods in a class to share the same name but differ by parameters, enabling the method to handle various tasks based on the arguments passed. For instance, an add method might add integers when given numbers or concatenate strings when given text, depending on its arguments. While many languages support overloading directly, Python does not. In Python, defining methods with the same name will override previous ones. Instead, Python handles varied inputs through default values, args, quarks, core conditionals within a single method, offering flexibility without traditional overloading. Practical example. In this example, the calculator class defines a method called add that uses default parameter values to simulate method overloading. The add method accepts up to three arguments A, B, and C. Here, B and C are optional and default to 0 if not provided. This setup allows the add method to handle different numbers of arguments while maintaining a single method definition, which is useful since Python does not support traditional method overloading. When we create an instance of calculator called calc, we can call the add method with varying numbers of arguments. For example, calling calc.add5 passes only the required A argument, so the method returns 5 as B and C default to 0. Calling calc.add5 10 provides values for A and B, resulting in 5, 10, 15. Finally, calling calc.add5 10, 15 uses all three arguments, yielding 5, 10, 15, 30. This example illustrates how Python can simulate method overloading by using default values for parameters, allowing the same method to operate flexibly with different argument patterns. This approach provides the benefits of overloading by adjusting behavior based on the number of arguments provided, making the code both efficient and adaptable. Question 16, what is abstraction and how is it implemented in Python? Abstraction is a core principle in object-oriented programming OOP that simplifies interaction with objects by hiding complex implementation details and exposing only essential features. The goal of abstraction is to allow users to work with an object at a high level, focusing on what the object does rather than how it does it. By masking unnecessary details, abstraction helps reduce complexity, making code easier to understand and use. This principle is especially valuable in large code bases where abstracting intricate operations into simple interfaces enhances readability, usability, and maintainability. In Python, abstraction is implemented primarily through abstract classes and interfaces. The ABC abstract base classes module allows developers to define abstract classes, which are classes that cannot be instantiated directly. Instead, abstract classes serve as blueprints, requiring subclasses to implement certain methods. Abstract methods are defined using the @abstract method decorator, which enforces that any subclass must provide its own version of the method. For example, an abstract class shape might define an abstract method calculate underscore area. Specific shapes like circle and rectangle would inherit from shape and implement calculate underscore area in ways unique to their geometry. By defining only the necessary interactions, abstraction allows users to work with objects through simple, consistent interfaces while the actual implementation remains hidden. This way, abstraction in Python not only simplifies the user experience but also enforces a structured approach to code design, supporting scalability and flexibility in OOP. Practical example. In this example, we use Python's abstraction capabilities to define a base class called shape with abstract methods. The shape class inherits from ABC, making it an abstract base class. which means it cannot be instantiated directly. Within shape, two abstract methods, area and perimeter, are defined using the abstract method decorator. These methods have no implementation in shape itself. Instead, they act as placeholders, requiring any subclass of shape to provide its own implementation for these methods. This approach allows shape to serve as a general blueprint for geometric shapes, ensuring that any specific shape subclass will have area and perimeter methods. The rectangle class is a subclass of shape that inherits from this abstract base class and implements the required methods. In its underscore underscore init method, rectangle accepts width and height as parameters, initializing these attributes to represent the dimensions of the rectangle. It then provides specific implementations of the area and perimeter methods. Area calculates the rectangle's area by multiplying its width and height, and perimeter calculates the perimeter by summing twice the width and twice the height. Creating an instance of rectangle such as rectangle 5, 10 allows us to use the area and perimeter methods with the dimensions specified. Calling rect.area returns 50 while rect.perimeter returns 30, demonstrating how the subclass fulfills the abstract requirements defined in shape. This example illustrates how abstraction, through abstract base classes and methods, enforces a consistent interface, allowing subclasses to implement their specific details while maintaining a common structure. Question 17: what is an interface and how can you implement it in Python? An interface defines a set of methods that a class must implement without detailing how they work. It acts as a contract, ensuring that any class implementing the interface follows a specific structure, allowing consistent interaction across different classes. In Python, interfaces are commonly implemented using abstract-based classes with abstract methods from the ABC module. By defining abstract methods in a base class, Python enforces subclasses to implement these methods. For example, an abstract class drawable with a draw method requires subclasses like circle and rectangle to implement their own draw logic, ensuring consistent behavior across implementations. Practical example. In this example, we create a drawable interface using an abstract base class which defines a structure that other classes must follow. The drawable class, marked as abstract by inheriting from a BC, contains two abstract methods, draw and resize. These methods are declared using the @abstract method decorator, indicating that any subclass of drawable must implement these methods to provide specific functionality. By defining drawable as an interface with required methods, we establish a contract that ensures all subclasses have draw and resize methods, enabling consistent interaction with various drawable shapes. The circle class implements the drawable interface, inheriting from drawable and providing concrete definitions for the draw and resize methods. The draw method outputs the circle's current radius, and the resize method adjusts the circle's radius by a given factor. This approach gives Circle the flexibility to perform specific actions while following the interface structure. Similarly, the Square class also implements the drawable interface with its own versions of the draw and resize methods. In this case, draw displays the square's side length, while resize updates the side length by the specified factor. This allows Square to follow the drawable contract while customizing functionality relevant to squares. To demonstrate polymorphic behavior, we create a list called shapes containing instances of circle and square. By iterating over shapes and calling draw and resize on each object, Python dynamically calls the appropriate method for each class, regardless of whether the object is a circle or a square. This flexibility highlights the power of interfaces as it allows for consistent interactions across different implementations, resulting in output like drawing a circle with radius 5 and drawing a square with side length 4. This example shows how Python's abstract classes serve as interfaces, providing a structured and predictable way to handle multiple object types with shared functionality. Question 18. What is the difference between an abstract class and an interface? Abstract classes and interfaces both provide a blueprint for classes, but they serve different purposes in object-oriented programming. Abstract classes can include both implemented and abstract methods, allowing subclasses to inherit shared functionality while enforcing a structure. They typically represent a strong user relationship, such as a shape abstract class with both a calculate underscore area method and a concrete display method. Interfaces, however, define only abstract methods, acting as a contract that ensures consistent methods across different classes without sharing other traits. For example, a drawable interface with draw and resize methods ensures that any class implementing it has these methods, regardless of class hierarchy. In Python, both concepts are implemented with abstract base classes, with interfaces often represented as abstract classes containing only abstract methods. The key between an abstract class and an interface. Purpose abstract classes and interfaces serve different objectives in object oriented programming. Abstract classes provide a base class with shared functionality that subclasses can inherit and extend. They allow for common behaviors to be defined in one place and reused. Interfaces, however, focus on defining a contract for methods that implementing classes must provide. This contract specifies what methods should exist but does not dictate how they should be implemented, allowing diverse classes to share the same structure. Implementation abstract classes can include both concrete implemented methods and abstract unimplemented methods. This flexibility enables abstract classes to offer default behavior while still requiring certain methods to be defined by subclasses. Interfaces, by contrast, typically contain only abstract methods without any implementation, serving purely as a structure that must be followed by any implementing class. Multiple inheritance due to Python's single inheritance model. A class can inherit from only one abstract class. This limitation makes abstract classes best suited for situations where a strict inheritance hierarchy is needed. Interfaces, however, can be implemented by multiple classes, allowing a class to adhere to multiple interfaces and simulate multiple inheritance. This flexibility makes interfaces valuable when classes need to share behavior patterns without being restricted to a single inheritance path. Usage abstract classes are ideal when you want subclasses to inherit some shared behavior in addition to a specific method structure. This allows subclasses to extend or override parts of the base functionality. Interfaces, on the other hand, are best used when you want different classes to follow the same structural contract without inheriting any behavior. They enforce consistency across classes while allowing complete freedom in implementing the method's functionality. Question 19. How does Python manage memory for objects? Python manages memory for objects using an efficient and automated system that handles memory allocation, tracking, and deallocation. When objects are created, memory is automatically allocated without the need for developers to manually specify or allocate memory. This automatic allocation simplifies object creation and allows developers to focus on coding rather than memory management. To free up memory when objects are no longer needed, Python employs a garbage collection system. Garbage collection helps prevent memory leaks by delocating memory occupied by objects that are no longer in use. Python's garbage collector continuously monitors objects, and when certain conditions are met, it frees up memory that is no longer needed. This process keeps memory usage efficient throughout the program's execution. A key component of Python's memory management is reference counting. Python keeps track of the number of references to each object each time an object is referenced. its count increases, and each time a reference is removed, the count decreases. When an object's reference count reaches 0, meaning it is no longer being used or referenced, Python knows it can safely deallocate that object's memory. This reference counting mechanism works in conjunction with garbage collection, helping Python to manage memory effectively by ensuring unused objects are removed from memory when they are no longer needed. Together, automatic memory allocation, garbage collection, and reference counting create a robust memory management system in Python that reduces the risk of memory leaks and improves program efficiency. Practical example. In this example, we demonstrate Python's memory management through reference counting and garbage collection. We begin by creating a list object A and using sys.getIfCount to check its reference count. The sys.getIfCount function returns the number of references to an object, including the temporary reference created by getIfCount itself, so we subtract 1 to get the actual reference count. Initially, A has a reference count of 1. We then create additional references to A by assigning B and C to the same list object. This increases the reference count each time a new variable references A, which we observe through sys.getIfCount. As expected, after assigning B and C to A, the reference count rises to 3. Adding another reference D raises the count to 4. Next, we delete references one by one, starting with B and then C, observing the reference count decrease accordingly. Each deletion removes a reference, reducing the reference count as Python tracks the number of active references to manage memory. We then create a circular reference by appending A to itself, so A now contains a reference to itself. This circular reference increases the reference count due to a pointing back to itself, which could ordinarily create a memory leak in systems without automatic garbage collection. Finally, we delete D and then A, removing all external references to the list object. With no external references, Python's garbage collector detects this circular reference and automatically cleans up the object during its next cycle. This example demonstrates how Python's reference counting and garbage collection handle memory efficiently, even in cases of circular references, by ensuring that unused objects are safely deallocated when they are no longer referenced. Question 20. How do underscore underscore str and underscore underscore undepar methods differ? In Python, the underscore underscore str and underscore underscore repr methods are special methods that define how an object is represented as a string, but they serve different purposes and are used in different contexts. Here's a detailed aspect-wise narration explaining the differences between underscore underscore str and underscore underscore at repr. The primary purpose of underscore underscore str is to provide a readable, user-friendly string representation of an object. It is designed with end users in mind, giving a clean and concise summary of the object's main features. In contrast, underscore underscore repr aims to give an unambiguous, detailed string representation intended for developers and debugging purposes. The goal of underscore underscore repr is to provide a more precise view of the object state, which is often useful for diagnosing issues or inspecting the object. Usage, the underscore 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 method is used when printing the object directly or when converting it to a string, as in print obj or str obj. This representation is intended to be clear and accessible to users. Meanwhile, underscore underscore repr is invoked in interactive interpreter sessions or when calling repr object. It is used primarily for debugging and typically displays information that is more technical and informative, making it helpful in development. Return preference underscore underscore str should ideally return a concise, easy to read description that provides a high level overview of the object. The underscore underscore repr method, on the other hand, is ideally suited to returning a string that could recreate the object if evaluated. often including additional details to give an accurate picture of the object state. Fallback: if underscore underscore str is not defined in a class, Python will use underscore underscore repr as a fallback, so the object still has a string representation when printed. However, if underscore underscore repr is not defined, Python defaults to a basic identifier that shows the object's class and memory address, offering minimal information about the object. Practical example. In this example, the person class defines both underscore 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 and underscore underscore repr methods, providing distinct representations for different purposes. When an instance of person is created with a name and age, such as person Alice 30, these methods allow us to view the object in both a user-friendly and a developer-oriented format. The underscore underscore star method is designed to return a simple, readable description of the person object, showing the name and age in a format that is easy to understand. When we call str person or simply print person, the underscore underscore str method is implicitly invoked, producing the output Alice 30 years old. This method makes the object's information more accessible, allowing it to be presented in a way that is useful for end users. The underscore underscore repr method, on the other hand, provides a more detailed and precise representation intended for developers. It returns the string person name Alice, age 30, which not only includes the object's attributes but also reflects its internal structure in a way that could recreate the object if evaluated. When calling repr person, Python invokes underscore underscore repr, displaying the object in this developer-friendly format. This example highlights the difference in purpose between underscore underscore str and underscore 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 repr underscore str focuses on readability for users, while underscore underscore and repr provides an unambiguous, informative view for debugging or development. By defining both methods, the person class offers flexible representation suitable for different contexts. Question 21. What is the difference between a static method and a class method? In Python, static methods and class methods are methods tied to the class rather than instances, but they differ in purpose and access. A static method defined with at static method is independent of both the class and instance. It acts like a regular function within the class namespace. Static methods don't take self or CLS as parameters and can't modify class or instance attributes. They're useful for utility functions related to the class conceptually. A class method defined with that class method takes CLS as its first parameter, giving it access to class level attributes and methods. This makes class methods ideal for operations that involve the class itself, such as creating instances in specific ways. In short, static methods serve as independent utilities, while class methods interact with and can modify the class. Here's an aspect-wise explanation of the differences between static methods and class methods in Python. Definition: static methods and class method defined differently in Python. A static method is marked with the @static method decorator, while a class method is defined using the @class method decorator. This distinction clarifies their intended roles and how they interact with the class. First parameter, a static method, does not take self the instance or sees the class as its first parameter, as it doesn't need to access or modify class or instance data. In contrast, a class method takes CLS as its first parameter, which represents the class itself, allowing it to interact with and modify class level attributes or methods. Access to class instance: static methods cannot access class or instance variables directly, as they are independent of both the class and its instances. Class methods, however, have access to class level attributes through CLS, enabling them to read or update class specific data. This capability makes class methods useful for operations that involve or affect the class as a whole. Purpose static methods are generally used for utility functions that are conceptually related to the class but don't require access to class or instance specific data. Class methods, on the other hand, are used for operations that involve the class as a whole, such as alternative constructors that create instances in specialized ways or perform class level operations. Call context, both static methods and class methods are called directly on the class itself, as in className.method. Static methods act as independent functions within the class namespace, while class methods can use scales to refer to the class context and modify its state. Question 22. How can you define and use static methods in Python? In Python, a static method is a method that belongs to a class but operates independently of the class itself and any of its instances. Unlike regular methods, static methods do not require self the instance or CLS the class as parameters, as they do not access or modify any instance specific or class specific data. This makes them ideal for utility functions that logically belong to the class but don't need to interact with its internal attributes. Static methods are defined using the add_static method decorator. This decorator informs Python that the method will not access or modify the class state, allowing it to be called directly on the class without needing an instance. For instance, if a class math operations includes a static method add_numbers, this method can be used to add two numbers without requiring any instance of math operations. The method could be called as mathoperations.add_numbers xy, making it accessible as a utility function within the class context. Static methods are useful for encapsulating functionality related to the class but independent of its specific data. By grouping related functions within a class, static methods help organize code logically while maintaining clear boundaries between operations that do and do not interact with class attributes. This enhances modularity and keeps utility functions neatly within the class to which they are conceptually related. Practical example. In this example, the math operations class demonstrates the use of static methods to perform mathematical calculations without accessing or modifying any instance or class-specific data. Two static methods, square and cube, are defined within the class to calculate the square and cube of a given number, respectively. Since these methods do not require access to class level data, they are decorated with that static method, allowing them to be called directly on the class without needing an instance. The square method takes a single parameter, number, and returns the square of the value by raising it to the power of 2. Similarly, the cube method calculates the cube of a given number by raising it to the power of 3. These calculations are purely functional and independent of any data within math operations, making static methods an ideal choice for their implementation. To use these static methods, we call them directly on the math operations class as mathoperations.square4 and mathoperations.cube3, providing the respective values as arguments. This produces the output 16 and 27 for the square of 4 and the cube of 3. By defining these operations as static methods within the mathOperations class, we keep the utility functions logically organized under a relevant class, enhancing modularity and maintaining clear boundaries between data-independent functionality and class or instance methods. Question 23. What are class variables and instance variables? In Python, class variables and instance variables are two distinct types of attributes that can be defined within a class, each with unique characteristics in terms of scope, purpose, and behavior across instances. Class variables are attributes that belong to the class itself rather than to any individual instance. They are defined directly within the class body, outside of any methods, and are shared among all instances of the class. This means that any change to a class variable affects all instances, as each instance accesses the same shared attribute. Class variables are typically used for data that should remain consistent across all instances, such as constants or settings that apply to the entire class. For example, if a car class has a wheels class variable set to 4, all instances of car will have 4 wheels by default. Instance variables, on the other hand, are unique to each instance of the class and are usually defined within the underscore underscore init method. These variables are prefixed by self, which ensures they are tied specifically to the instance that creates them. Each instance of the class can have its own set of values for instance variables, making them suitable for storing data that varies across objects. For example, each car instance might have its own color and model, which differ from one car to another. Changes to an instance variable affect only that particular instance, allowing each object to maintain its own unique state. In summary, class variables provide shared data accessible by all instances, while instance variables store data specific to each object, allowing flexibility and individuality among instances of the same class. Practical example. Uh, in this example, the car class demonstrates the difference between class variables and instance variables. The class variable wheels is defined directly within the class, outside any methods, and is shared across all instances of car. This variable represents a property common to all cars, the number of wheels, which is set to 4. Since wheels is a class variable, it can be accessed through the class itself, e.g. car.wheels, and is the same for every instance created from the class. Within the underscore underscore init method, two instance variables make and model are initialized. These instance variables are specific to each car object and they store unique information about each car's brand and model. When an instance of car is created, such as car 1 for a Toyota Camry or car 2 for a Honda Civic, the make and model values are set uniquely for each instance. We first print the class variable wheels by accessing it directly through the car class, which outputs wheels on all cars. For this shows that the class variable is accessible without needing to instantiate the class. Next, we create two instances, car 1 and car 2, and print the wheels attribute through each instance. Since wheels is a class variable, it displays the same value 4 for both car 1 and car 2, showing that it is shared among all instances. This example illustrates that class variables provide shared data for the entire class, while instance variables offer unique attributes specific to each object created from the class. Question 24, explain at class method and its usage. The at class method decorator in Python is used to define a method that is bound to the class rather than any specific instance. Unlike regular instance methods, which receive self as their first parameter representing the instance, a class method takes CLS as its first parameter, representing the class itself. This distinction allows class methods to access and modify class level attributes directly, making them ideal for operations that involve the class as a whole rather than individual instances. One common use of class methods is to serve as alternative constructors. In addition to the usual underscore underscore init constructor, a class method can create instances in different ways or with different initial setups. For example, a date class might have a standard constructor that takes day, month, and year as parameters, but a class method could be used to create a date instance from a formatted string like EMEM and DD. This alternative constructor, defined as a class method, would pass the string, extract the day, month, and year, and then return a new instance. By using add class method, developers can add flexibility to how instances are created and manipulated, providing a structured way to handle operations that pertain to the entire class. Additionally, class methods can be called on both the class itself, e.g., classname.method, and on instances, though they always operate at the class level rather than the instance level. This makes a class method a powerful tool for managing class level data and creating structured, reusable constructors or factory methods. Practical example. In this example, the car class illustrates the use of class methods for managing class level data and providing alternative constructors. A class variable, total underscore cars, is defined to keep track of the total number of car instances created. Each time a new car is instantiated using the underscore underscore init method, this counter increments by 1, updating the total count of cars. The car underscore count method, decorated with at class method, is a class method that returns the current count of all cars created. It takes CLS as its first parameter, allowing it to access the class variable total underscore cars directly. By calling car.car underscore count, we get a message displaying the total count, which reflects the number of car instances created so far. This demonstrates how class methods can interact with and provide information about class level data, giving us a simple way to check the total cars without needing an instance. Another class method from underscore string acts as an alternative constructor, allowing us to create a car instance from a formatted string. This method takes a string argument car underscore string, which contains the car's make and model separated by a -eg Ford Mustang. Inside the method, the string is split into make and model components, which are then passed to CLS make model to create a new car instance with these values. This approach provides a flexible way to create instances from alternative formats, extending the functionality of the car class. By creating instances car1 and car2 with the standard constructor and car3 with the from underscore string class method, we see that the class level counter total underscore cars updates accurately each time. This example highlights how class methods through at class method offer convenient ways to manage class level data and create instances in varied formats, enhancing the utility and flexibility of the class design. Question 25. What is the purpose of underscore underscore new and how does it differ from underscore underscore init? In Python, underscore underscore new and underscore underscore init are both involved in object creation but serve different purposes. Underscore underscore new is the first method called responsible for allocating memory and creating a new instance. It returns this instance and is mainly customized when specific control over instance creation is needed, such as in singletons or with immutable types. After underscore underscore new completes, underscore underscore init is called to initialize the instance attributes and set up its state. While underscore underscore new handles creation, underscore underscore init configures the object, and typically only underscore underscore init is overridden unless special handling is required during instantiation. Key differences between underscore underscore new and underscore underscore init in Python. Purpose. The primary role of underscore underscore new is to create a new instance of the class. It is responsible for allocating memory and instantiating the object, setting the stage for further initialization. In contrast, underscore underscore init is designed to initialize the instance's attributes and configure its state once the instance has been created. While underscore underscore new is about creation, underscore underscore init focuses on customization of the newly created instance. Invocation underscore underscore new is automatically called first when a new instance of a class is created, before underscore underscore init. This ordering allows underscore underscore new to create and return the instance, which is then passed to underscore 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 init for initialization. Thus, underscore underscore new sets up the raw object, and underscore underscore init finalizes its configuration. Return type, the underscore underscore new method must return a new instance of the class or potentially an instance of a different class if customized. This returned instance is what underscore underscore init receives for further setup. Conversely, underscore underscore init doesn't return anything, it always returns none, as its role is purely to configure the already created instance. Use cases underscore underscore new is commonly used in advanced programming scenarios such as metaclass programming or when subclassing immutable types like int or str. These cases require control over the creation process itself. Meanwhile, underscore underscore init is typically used for setting initial values to attributes and configuring instance specific settings, making it more commonly overridden in custom classes. Practical example. In this example, the custom class demonstrates the use of both underscore underscore new and underscore underscore init methods, highlighting their distinct roles in object creation and initialization. The underscore underscore new method is defined first and is responsible for creating the new instance. When we attempt to create an instance of custom class, underscore underscore undo is called first, printing creating a new instance of custom class. Within underscore underscore new, the super dot underscore underscore new CLS call is used to actually create the instance by invoking the underscore underscore new method of the parent class object, which allocates memory and returns a new instance. This instance is then passed on to underscore underscore init for further setup. After underscore underscore new returns the new instance, the underscore underscore init method is automatically invoked to initialize it. In this case, underscore underscore init prints initializing the instance and assigns the value attribute to the instance. This value is provided as an argument during object creation, allowing us to set initial attributes specific to this instance. Finally, when we print obj.value, it outputs value attribute 42 confirming that the value attribute has been successfully set by the underscore underscore init method. This example illustrates the flow from underscore underscore new to underscore underscore init underscore underscore new creates and returns the instance, while underscore underscore init sets up its initial state, demonstrating how these methods work together in Python's object creation process. Question 26. Explain how you would use operator overloading in Python. Operator overloading in Python is a feature that allows custom objects to interact with built-in operators such as EAC by defining special methods within the class. This means that we can customize how these operators behave when applied to instances of our own classes, giving them the same intuitive functionality as built-in data types like integers, strings, or lists. By using operator overloading, we enable our objects to respond to operators in a way that aligns with their purpose, making them easier to use and more readable. Key special methods for operator overloading in Python. In Python, operator overloading is achieved through special methods, also known as magic or dunder double underscore methods, which can be defined within a class. These methods enable custom classes to respond to standard operators like AND, comparison operators such as AND. By implementing these methods, we can control how instances of our classes interact with various operators, enhancing usability and making custom objects behave more intuitively. Arithmetic operators. For arithmetic operations, Python provides specific methods to overload each operator. For example, underscore underscore add self other is used to overload the operator, allowing us to define how two instances of the class are added. Similarly, underscore underscore sub self other underscore underscore mul self other and underscore underscore trueDiv self other correspond to subtraction, multiplication, and division respectively. These methods let custom objects perform mathematical operations in a natural, readable way. Comparison operators allow us to define how instances of a class are compared. The underscore underscore eq self other method overloads the operator, specifying when two instances are considered equal. Other methods include underscore underscore any self other for, underscore underscore lt self other for underscore underscore gt self, other for underscore underscore self other for, and underscore underscore g self other for. By implementing these methods, we can control relational comparisons between objects, making it easier to handle logical conditions involving custom instances. Unary operators act on a single operand, such as the negation and positive operators. The underscore underscore next self method defines how the operator works for the class, while underscore underscore post self does the same for. This allows us to define custom behavior for unary operations, enhancing control over how instances respond to sign-based modifications. Together, these special methods allow custom objects to interact seamlessly with standard operators, creating a more intuitive experience and making custom classes as versatile and expressive as built-in types. Practical example. In this example, the vector class demonstrates operator overloading to allow vector objects to interact with standard operators like AND. By implementing special methods such as underscore underscore add, underscore underscore sub, and underscore underscore eq, we enable instances of vector to behave like mathematical vectors, enhancing the readability and functionality of the class. The underscore underscore add method overloads the operator, allowing two vector instances to be added together. Within underscore underscore add, we check if the other operand is also a vector, and if so, return a new vector with the sum x and y components. This allows expressions like v1, v2, where v1 and v2 are vector objects, to produce a new vector as expected in vector addition. Similarly, the underscore underscore sub method overloads the operator to handle vector subtraction by creating a new vector with the x and y components subtracted. The underscore 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 eq method overloads the operator, defining equality for vector objects. It checks whether both x and y components of two vectors are equal, allowing expressions like v1, v3 to return true if the vectors have identical components and false otherwise. Finally, the underscore underscore str method is overridden to provide a readable string representation of vector instances. This ensures that when a vector is printed, it outputs in a friendly format like vector2, 4 instead of a generic object reference. Using this setup, we create instances v1, v2, and v3 and perform operations such as addition v1, v2, subtraction v1, v2, and equality comparison v1, v3. Each operation behaves naturally and intuitively due to the overloaded operators, making vector objects easier to work with in mathematical context. This example highlights how operator overloading improves the usability and expressiveness of custom classes in Python. Question 27. What is duck typing and how is it relevant to Python OOP? Duck typing in Python is a concept where an object's suitability for an operation is based on its methods and properties rather than its specific type. The principle is if it looks like a duck and quacks like a duck, it probably is a duck. This means that if an object has the required behavior, such as a specific method, it can be used regardless of its class. In Python, duck typing enables polymorphism by focusing on what an object can do rather than enforcing strict type checks. For example, if a function expects an object with the right method, it doesn't matter if the object is a file or something else as long as it has right. This flexibility allows more reusable and adaptable code, emphasizing behavior over class structure, and is fundamental to Python's dynamic and polymorphic design. Practical example. In this example, we demonstrate duck typing in Python, where an object's suitability is based on its behavior rather than its specific type. Here we define two classes, duck and person. Both classes implement a quack method, but their implementations differ. The duck class's quack method returns quack. Quack to represent the typical sound a duck makes, while the person class's quack method returns "I'm quacking like a duck" to show that even though a person is not a duck, they can mimic the behavior of one. The make underscore it underscore quack function is designed to take any object as long as it has a quack method, regardless of the object's type. In Python, this is possible due to duck typing. Make underscore it underscore quack does not check if the object is an instance of duck or any specific class. Instead, it simply calls the quack method on the given object, trusting that the object will provide the required behavior. We create instances of both duck and person and pass them to make underscore it underscore quack. In each case, make underscore it underscore quack successfully calls the quack method on both duck and person, producing the expected output based on each class's implementation. This example illustrates duck typing in action. As long as an object quacks provides the quack method, it can be treated as duck-like, emphasizing behavior over type and enhancing flexibility in Python code. Question 28. What is a singleton pattern and how do you implement it in Python? The singleton pattern is a design pattern that restricts the instantiation of a class to a single instance, ensuring that only one object of the class exists throughout the application's lifecycle. This single instance serves as a global access point, allowing other parts of the application to access the same instance whenever needed. The singleton pattern is particularly useful when managing shared resources or configurations such as a database connection, logging system, or configuration manager, where having multiple instances could lead to inconsistencies or unnecessary resource consumption. In Python, implementing the singleton pattern can be done in several ways. One common approach is to override the classes underscore 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 new method, which is responsible for creating new instances. By modifying underscore underscore new, we can ensure that the class only creates a new instance the first time it's called. For subsequent calls, the class will return the same instance, effectively making it a singleton. Another approach uses a class variable to store the instance and a class method to manage instantiation, only creating the instance if it doesn't already exist. Python's add class method decorator is often helpful in this method as it allows access to class variables and methods without requiring an instance. The singleton pattern offers a controlled way to manage instances in a system that needs only one point of access, promoting resource efficiency and consistency across the application. By ensuring a single instance, it prevents the duplication of resource-intensive objects and provides a structured way to share data or resources globally. Practical example: bus. In this example, the singleton class demonstrates the singleton pattern, ensuring that only one instance of the class can exist. A class variable underscore instance is used to store the single instance of singleton. In the underscore underscore new method, we check whether underscore instance is already set. If underscore instance is none, indicating that no instance has been created yet, underscore underscore new calls super dot underscore 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 new CLS to create and assign a new instance to underscore instance. If an instance already exists, underscore underscore new simply returns the existing underscore instance, ensuring no additional instances are created. The underscore underscore init method accepts a value parameter, which is used to initialize the value attribute of the singleton instance. However, because the singleton instance is only created once, any subsequent calls to initialize another singleton object only modify the value of the existing instance without creating a new one. When we create two singleton instances, singleton 1 and singleton 2, both point to the same underlying object. As verified by the singleton 1 is singleton 2 check, which returns true. Although singleton 1 was initially created with value 10, setting singleton 2 to 20 updates the value attribute across both references, reflecting the singleton's shared state. This example shows how the singleton pattern works. It provides a single, consistent instance of singleton throughout the program, ensuring all references access the same object and share the same data. Question 30. Explain the purpose of underscore underscore len, underscore underscore getim, and underscore underscore setim. In Python, the underscore underscore len, underscore underscore getim, and underscore underscore setim methods allow custom objects to behave like built-in collections such as lists or dictionaries. The underscore underscore len method defines how len object operates, returning the number of items in an object, which is essential for collection like classes. The underscore underscore getitem method enables item access using indexing or slicing, allowing retrieval of elements with obj key, while underscore underscore setitem allows item assignment with obj key value, enabling direct updates to elements within the object. Implementing these methods allows custom classes to support Python standard syntax for length checking, indexing, and assignment, making them more intuitive and flexible. Practical example. Then in this example, the custom list class showcases how the special methods underscore underscore getitem, underscore underscore setitem, and underscore underscore len can be used to make a custom class behave like a built-in list. The underscore underscore init method initializes the custom list instance with an attribute items, which is a list passed during object creation. This list holds the actual data that the custom list will manage. The underscore underscore getitem method is implemented to allow index-based access, just like a regular list. When we call list1, Python uses underscore underscore getitem to return the element at index 1 in the items list, which initially outputs 2. Next, the underscore underscore setitem method allows us to modify items at a specified index. When we assign list 120, underscore underscore setitem updates the value at index 1 in items to 20. This change is confirmed when we print list 1 again, showing the updated output of 20. Finally, the underscore underscore len method defines how length list works, returning the number of elements in items. Calling length list thus outputs 3, the number of elements in the original list 1, 2, 3. Together, these methods make custom list operate seamlessly with indexing, assignment, and length checking, demonstrating how custom classes can mimic the behavior of built-in list structures by implementing these special methods. Question 31. How do you implement a custom iterator class? In Python, an iterator is an object that allows sequential access to its elements, making it especially useful for looping structures. To implement a custom iterator, we define a class that includes two special methods underscore underscore iter and underscore underscore next. The underscore underscore iter method returns the iterator object itself and is called once at the beginning of an iteration, setting the stage for the sequence of elements to follow. This method essentially signals that the object is ready to be iterated over and provides the initial state for the iteration. The underscore underscore next method is responsible for returning the next element in the sequence on each call. Each time the loop requests the next item, underscore underscore next yields the next element in the sequence. When the iterator reaches the end of its elements, underscore underscore next faces stop iteration exception, signaling that there are no further elements to return and effectively ending the iteration. This exception handling is crucial as it prevents infinite loops and lets the calling code know that the iteration is complete. Practical example. In this example, the counter class demonstrates how to create a custom iterator in Python, enabling us to generate a sequence of numbers from a specified start to an end value. The class initializes with two attributes: current, which tracks the current count, and end, which sets the upper limit for the counter. The underscore underscore return method is defined to return the iterator object itself, allowing the counter instance to be used directly in a loop. This method is called once at the start of the iteration, setting up the object to be iterated over. The core of the iteration logic is in the underscore 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 next method, which determines what happens each time the loop requests the next item. Inside underscore underscore next, we check if the current count is less than or equal to end. If it is, we store the current value in num, increment current by 1, and return num. This provides the next item in the sequence on each iteration. Once current exceeds end, underscore 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 next raises a stop iteration exception, signaling that the iteration is complete. When we create an instance of counter with start 1 and end 5, we can iterate over it with the for loop. Each call to underscore underscore next returns the next number in the sequence, resulting in an output of 1, 2, 3, 4, 5. This example illustrates how defining underscore underscore iter and underscore 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 next enables the counter class to function as a custom iterator, providing controlled sequential access to a defined range of numbers. Question 32. What is the difference between composition and inheritance? Composition and inheritance are OOP principles for structuring the relationships between classes. Inheritance creates and is a relationship where a subclass inherits from a superclass, useful for hierarchical relationships. Composition creates A has a relationship where one class contains another, allowing for flexible modular design. Inheritance is ideal for shared hierarchies, while composition is preferred for reusing functionality without extending a base class. Comparison of composition and inheritance in Python. Definition: composition and inheritance establish different types of relationships between classes. Composition forms a has a relationship where one class contains instances of other classes as attributes. In contrast, inheritance creates an is a relationship where a subclass derives from a superclass inheriting its attributes and methods. Purpose composition is used to build complex types by combining objects of other classes, making each part a component within the containing class. This allows a class to use functionalities from various classes without inheriting from them. Inheritance, on the other hand, allows a class to extend or modify the behavior of an existing class, creating a subclass that retains the properties and behaviors of the superclass while potentially adding new functionality. Code reuse. Both composition and inheritance promote code reuse, but they do so in different ways. Composition achieves code reuse by including other classes as components, allowing access to their functionality without extending them. Inheritance promotes code reuse by letting a subclass inherit properties and methods from a superclass, effectively extending the existing class. Flexibility: composition offers more flexibility because it allows modifying or replacing components without altering the class structure. This makes it easier to adapt or extend functionality as needed. Inheritance is less flexible since changes to the superclass affect all subclasses that inherit from it, potentially impacting the entire class hierarchy. Use case composition is generally preferred when you want to include functionality from multiple classes without establishing a hierarchy, making it ideal for scenarios where reusable components are needed without a strict relationship. Inheritance is more suitable when there is a clear hierarchy and shared behavior among classes, allowing subclasses to represent specialized versions of the superclass. Practical example. In this example, the car class demonstrates a combination of inheritance and composition, showing how both principles can be used effectively in a single class. The vehicle class serves as the base class, with attributes make and model representing the vehicle's brand and model. It also includes a start method, which outputs a message indicating that the vehicle is starting. By inheriting from vehicle, car establishes an is a relationship, meaning a car is a type of vehicle, and thus it inherits the properties and behaviors defined in vehicle. In addition to inheritance, car also uses composition by including an instance of the engine class as an attribute. The engine class, separate from vehicle, has an attribute horsepower and its own start method, which outputs the engine's horsepower when it starts. This composition has a relationship where a car has an engine, enabling car to utilize the specific functionality of the engine class without inheriting from it. In the car class's start method, both inheritance and composition are put into practice. First, super.start calls the start method from vehicle, which prints a message indicating that the car as a vehicle is starting. Then self.engine.start calls the engine instance start method, adding details about the engine's horsepower. Finally, the drive method in car showcases additional behavior unique to cars, indicating that the car is driving. When we create a car instance and call car.start, it outputs messages from both vehicle and engine, demonstrating how car inherits vehicle properties and incorporates engine functionality through composition. This example highlights how inheritance can establish class hierarchy, while composition can modularly extend functionality, providing a robust and flexible design. Question 33, explain the term association in OOP with an example. In object-oriented programming OOP, association is a relationship between two independent classes that enables one object to use or interact with another. Unlike inheritance or composition, association does not establish a strict dependency. Instead, it represents a loosely coupled uses A relationship where one class utilizes the functionality of another without necessarily owning it or being tied to it permanently. This means that each associated object can exist independently of the other, allowing for greater flexibility and modularity in code design. Association can be unidirectional or bidirectional. In a unidirectional association, only one object is aware of the other and can interact with it. For example, a student class might have a reference to a library class, allowing a student to borrow books. However, the library class does not need to know each individual student, creating a one-way interaction. In a bidirectional association, both objects are aware of and can interact with each other. For instance, in a teacher-student relationship, a teacher class might maintain a list of student objects to keep track of students, while each student class could also keep a reference to their teacher. This type of relationship enables interaction without strong dependencies, supporting modular design. By using association, we allow objects to interact naturally while preserving their independence, enhancing code organization and usability in scenarios where classes need to cooperate without forming rigid hierarchies or dependencies. Practical example. In this example, the library and book classes illustrate the concept of association in object-oriented programming. The library class represents a library with attributes name, the library's name, and books a list to store book objects. The add underscore book method allows the library to associate book instances with itself by adding them to the books list. Meanwhile, the list underscore books method iterates over this list, calling each book's get underscore details method to display its title and author. The book class representing individual books has attributes title and author with the get underscore details method to return these details in a formatted string. This method is used by library to retrieve information about each book without requiring library to manage book specific details directly. In this association, library and book have a loosely coupled relationship. The library uses the book instances, but each book object exists independently and could be used by other classes as well. Additionally, this association is unidirectional. The library class knows about book instances and interacts with them, but book does not need to know about library. This setup reflects a typical user's A relationship, where library relies on book objects to function but does not tightly bind itself to them, supporting modular and flexible code design. When we create two book instances and add them to the library instance, calling list underscore books produces a listing of books in the library, showing how association allows the library to use and organize books effectively. Question 34. What is aggregation in Python OOP? In object-oriented programming OOP, aggregation is a type of association that represents a has a relationship, specifically a whole part relationship where one class includes another as a part, but without owning it. Unlike composition, where the part object's lifetime is strictly dependent on the whole object, aggregation allows the part to exist independently. This means that even if the whole object is deleted, the part can continue to exist and be used elsewhere in the program. For example, a team class might include player objects as members, but each player can also exist outside of that specific team. If the team object is removed, the player objects remain unaffected and can even join other teams. Aggregation is useful in cases where the relationship is significant, but the contained objects, the parts, have a standalone existence and are not exclusively tied to the whole. This design approach promotes flexibility as it allows classes to collaborate without tightly coupling their life cycles, making the code more modular and reusable. Aggregation is ideal when creating systems where objects are functionally related but should maintain their independence. Practical example. In this example, the department and employee classes demonstrate aggregation in Python OOP, where a department aggregates employees without owning them exclusively. The department class represents a department with attributes depth underscore name its name and employees a list to hold employee objects associated with the department. The add underscore employee method allows us to add employee instances to this list, and the list underscore employees method iterates through the list, printing each employee's details. The employee class represents individual employees with attributes name and position. It includes a get underscore details method to return these details in a formatted string. Notably, the relationship between department and employee is a form of aggregation rather than composition, meaning each employee can exist independently of department. For instance, even if the department instance is deleted, each employee can still function or be assigned to a different department. Aggregation here represents a hazard relationship where a department has employees but does not own their life cycle. When we create two employee instances, employee 1 and employee 2, and add them to the department instance depth, we can call depth.list underscore employees to output the details of employees in that department. This example highlights aggregation, allowing department and employee to interact without creating a strict dependency, promoting flexibility and independence in object relationships. Question 35. How would you handle exceptions within class methods? When handling exceptions within class methods, the goal is to ensure the method manages potential errors gracefully, maintaining program stability and delivering clear error messages to the user if something goes wrong. This is achieved by using Python's try and except blocks to handle exceptions that may arise during method execution. Wrapping code that may trigger an error within a try block allows the program to attempt execution, while one or more except blocks can capture and handle specific exceptions if they occur. For example, a method reading from a file could catch file in a found error and alert the user if the file doesn't exist, preventing the program from crashing. Additionally, class methods can raise custom exceptions to convey more meaningful messages. This allows us to signal specific errors related to the class's functionality, such as validation errors, using informative custom error types. This approach improves the user's understanding of what went wrong, making debugging easier. Furthermore, the finally block can be used within the method to perform cleanup actions like closing files or releasing resources that should run regardless of whether an error occurs, ensuring resource management. The optional else block provides an area for code that should only execute if no exceptions are raised, allowing for clearer control over the flow of logic. This structured approach to exception handling within class methods allows developers to control error scenarios thoughtfully, resulting in robust, user friendly code that maintains function continuity even in the face of unexpected issues. Practical example. In this example, the bank account class demonstrates how to handle exceptions within class methods to ensure error-prone operations like deposits and withdrawals are managed smoothly and errors are communicated clearly to the user. The bank account class includes two main methods, deposit and withdraw, both of which check for potential issues that might occur during transactions. In the deposit method, a value error is raised if a non-positive amount is provided, enforcing that only positive deposits are accepted. If the amount is valid, it adds to the balance and outputs the updated balance. The withdraw method incorporates exception handling with a try except finally structure. It first raises a value error if the withdrawal amount is non-positive. It also checks if the withdrawal amount exceeds the current balance, in which case it raises a custom insufficient funds error, defined at the start as a subclass of exception. In the except blocks, value error and insufficient funds error are handled separately, printing informative error messages for each type of issue. This allows for specific error handling based on the issue encountered, whether it's an invalid amount or insufficient funds. Finally, a finally block is included to output transaction completed regardless of the outcome, providing consistent feedback after each operation. This example shows how to handle different error scenarios within class methods, giving users clear and relevant error messages while ensuring the program remains stable and responsive. Question 36. How do decorators relate to OpenPython? In Python, decorators are functions or classes that allow us to modify or extend the behavior of other functions or methods without altering their original structure permanently. In object-oriented programming, decorators are particularly useful for enhancing the functionality of class methods, instance methods, or even entire classes in a modular way. By applying a decorator, we can add pre and post processing steps, enforce access control, implement logging, or handle caching within methods, all while keeping the original method code clean and focused on its primary purpose. When used in OOP, decorators enable us to add reusable functionality across different methods or classes without embedding repetitive code in each one. For instance, we can create a decorator that logs method calls, then apply it to multiple methods across classes to standardize logging without writing separate logging statements within each method. This approach allows us to separate core logic from auxiliary functionality, making code more modular, readable, and maintainable. Decorators are also instrumental in enforcing constraints like user authentication or data validation by wrapping methods with additional behavior. This flexibility makes decorators a powerful tool in Python's toolkit as they support clean, reusable, and adaptable designs by extending behavior without directly modifying the underlying code. Practical example. In this example, we use a decorator called log underscore execution to extend the behavior of methods within the calculator class. The log underscore execution decorator is designed to log the execution details of any function or method it creates. It starts by defining an inner function wrapper, which wraps the original function funcs, allowing additional behavior before and after the function executes. Inside wrapper, print statements are used to log the name of the function along with its arguments and keyword arguments before calling the function itself. Once the function completes, wrapper logs the returned result, providing a detailed view of the method's execution. To apply this decorator to methods in calculator, we add at log underscore execution above each method definition. When we call calc.add 5, 3, the log underscore execution decorator logs the execution of add, displaying the method name arguments 5, 3, and the result 8. Similarly, calling calc.subtract 10, 4 logs the details of subtract, showing the arguments 10, 4, and the result 6. Using decorators in this way enhances the methods without altering their original code, making it easy to add functionality like logging across multiple methods in a consistent, reusable manner. The decorator pattern also promotes separation of concerns by isolating logging functionality from core business logic, resulting in cleaner, more maintainable code. This approach is particularly useful in object-oriented programming for adding cross-cutting concepts like logging, error handling, or access control in a modular and reusable way. Question 37. What is a metaclass and how does it affect class creation? In Python, a metaclass is essentially a class of a class, meaning it defines the behavior of classes themselves rather than instances of those classes. While a regular class defines the structure and behavior for the objects it creates its instances, a metaclass defines the structure and behavior of the class itself. This allows metaclasses to influence and customize how classes are created, controlling aspects like modifying or adding class attributes, enforcing design patterns, or automatically injecting special methods into the class. Metaclasses are specified using the metaclass keyword in the class definition. When a class is created, Python looks for a metaclass, either explicitly defined or inherited, to oversee the creation process. Customizing a metaclass often involves defining the underscore underscore new or underscore underscore init methods in the metaclass, allowing it to intercept and modify the class at the time of its creation. This can be powerful for advanced use cases such as automatically adding validation methods, enforcing naming conventions, or ensuring certain base classes are present. Practical example. In this example, we define a custom metaclass, custom meta, to modify the process of class creation. The custom metaclass inherits from Python's built-in type class and overrides the underscore underscore a new method, which is responsible for creating new class objects. Within underscore underscore new, we add custom functionality by printing a message creating class name to indicate when a new class is being created. Additionally, we modify the class dictionary class underscore dict by adding a greet method, which is a lambda function that returns a greeting string containing the class name. This added method becomes part of any class created using custom meta. When we define myClass with metaclass custom meta, Python uses custom meta to control the creation of myClass. This means that during myClass creation, the underscore underscore new method in custom meta is invoked, which prints the creation message and adds the greet method to myClass. As a result, when we create an instance of myClass and call instance.greet, it returns hello from myClass because the greet method was injected by the metaclass. This example illustrates the power of metaclasses in Python. By defining custom behavior in underscore underscore new or underscore init of a metaclass, we can modify or extend classes during their creation, adding methods, enforcing conventions, or setting additional attributes automatically. While metaclasses are not common in everyday programming, they are particularly useful for building frameworks and ensuring that classes meet specific requirements or behaviors, providing deep customization and control over class design. Question 38 explain the underscore underscore call method and its use cases. The underscore underscore call method is a special method in Python that makes an instance of a class callable, allowing it to be used like a function. When the underscore underscore call method is defined within a class, it enables instances of that class to be called with parentheses as if they were functions. This is particularly useful in scenarios where you want an object to represent a specific operation or behavior that can be invoked directly, such as in cases of configuration objects, mathematical operations, or command style classes. For example, if we define a underscore underscore call method in a multiplier class, instances of multiplier can be called with a number as an argument, multiplying that number by a predefined factor stored within the instance. This approach allows for a more intuitive syntax when using the object, as it can be invoked directly with instance value, making it feel more function-like. Practical example. In this example, the multiplier class demonstrates how the underscore underscore call method can make an instance behave like a function. The multiplier class initializes with an attribute factor, which sets the multiplication factor for each instance. The key functionality is in the underscore underscore call method, which takes a parameter x and returns the product of x and the instance factor. Defining underscore underscore call allows instances of multiplier to be invoked directly as if they were functions. When we create an instance double multiplier 2, it stores 2 as the multiplication factor. Calling double 5 uses the underscore 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 call method, where x is 5 and returns 5 2, resulting in 10. This behavior allows the double instance to function like a multiplier function that always doubles its input, enhancing readability and providing a cleaner, function-like syntax for repeated operations. Using underscore underscore call is particularly helpful when an object represents an operation or configuration that can be reused with different inputs. Here, multiplier instances serve as scalable objects that encapsulate a specific behavior, in this case, scaling numbers by a factor, allowing easy direct invocation and a more intuitive interface for users. Question 39 explain the concept of underscore underscore slots in Python and why you might use it. The underscore underscore slots attribute in Python is a special feature used to define a fixed set of attributes for instances of a class, optimizing memory usage and potentially improving performance. Normally, Python stores instance attributes in a dictionary called underscore underscore dict, which provides flexibility by allowing any number of attributes to be dynamically added or modified. However, this flexibility comes at the cost of additional memory overhead, especially for classes that will create many instances. By using underscore underscore slots, you can specify a fixed list of attribute names that instances of the class are allowed to have. This prevents Python from creating a underscore underscore dict for each instance, reducing memory consumption as each instance will only allocate space for the predefined attributes. This approach is particularly beneficial in memory-intensive applications or situations where the class will be instantiated thousands of times, such as in data processing or scientific computations. Practical example. In this example, we compare the memory usage of two classes, regular person, slot person, to demonstrate the effect of using underscore underscore slots. The regular person class is a standard Python class that does not define underscore underscore slots, so each instance includes the underscore underscore undict to store its attributes. This dictionary provides flexibility, allowing attributes to be added or modified dynamically. However, it also requires additional memory to maintain, which can be inefficient if the class will have many instances. The slot person class, on the other hand, defines underscore underscore slots name, age, which explicitly limits instances to only name and age attributes. By using underscore underscore slots, Python does not create underscore underscore dict for each instance, thereby reducing memory usage. This approach optimizes memory efficiency because each instance only stores space for the attributes defined in underscore underscore slots rather than an expandable dictionary. When we create instances of regular person and slot person and check their memory sizes using sys.getSizeOf, we see that slot person instances consume less memory than regular person instances. This memory reduction is particularly useful in applications where many instances of a class will be created, such as in data-heavy applications or large-scale processing. While underscore underscore slots provides memory and performance benefits, it does limit flexibility as adding or modifying attributes outside those defined in underscore underscore slots will raise an attribute error. This example shows how underscore underscore slots can be a powerful tool for efficient memory management in Python when dynamic attribute flexibility is not required. Question 40, explain the property decorator and its benefits. The add property decorator in Python is a built-in feature that allows you to define methods that can be accessed like attributes, providing a clean and intuitive way to manage access to an object's data. By using add property, you can create getter, setter, and deleter methods for an attribute, which enables controlled access to that attribute while maintaining a simple attribute-like syntax for users of the class. This allows you to encapsulate data, implement validation, or add extra processing when attributes are accessed or modified without altering the external interface of the class. For example, you might use a property to define a temperature attribute in a class representing a thermostat. By using a property as a getter, you can retrieve the temperature. With the corresponding at temperature.setter method, you can set the temperature with validation or other adjustments, ensuring that only valid values are assigned. This approach allows you to enforce constraints or calculate derived values transparently, all while giving the class's users a simple, intuitive way to interact with the attribute. Practical example. In this example, the rectangle class demonstrates the use of the property decorator to manage attribute access and validation. The class initializes with underscore width and underscore height attributes, which are considered protected by convention indicated by the underscore. Instead of directly exposing these attributes, we define width and height as properties with both getter and setter methods, allowing controlled access. The at property decorator makes width and height accessible like attributes, so rect.width retrieves underscore width via the getter and rect.width value updates it using the setter. The setter method for width checks if the assigned value is negative, raising a value error if it is, thus enforcing a positive value constraint. The same pattern is applied to height, providing a consistent approach to validation and protecting the integrity of the data. Additionally, we define an area property using a property without a setter, making area a read-only attribute that calculates and returns the rectangle's area. Since area depends on width and height, it updates dynamically if either dimension changes. Using a property allows rectangle to manage attribute validation and encapsulation in a way that's seamless for users who can interact with width, height, and area as if they were regular attributes. This approach not only hides implementation details but also adds flexibility, such as enforcing constraints without affecting the class's external interface. For example, attempting to set rect.width to a negative value raises a descriptive error showing how properties support both usability and data integrity in class design. Question 41. How do you implement method resolution order and row in Python? In Python, method resolution order row is the sequence in which Python looks for methods or attributes when a class is part of a complex inheritance hierarchy, especially in cases of multiple inheritance. Bro ensures that Python searches for attributes or methods in a predictable and consistent order, which is crucial when working with multiple base classes. Python's follows the C3 linearization algorithm, also known as C3 superclass linearization, which calculates the order in a way that respects both inheritance and the method resolution order of parent classes, creating a consistent hierarchy. Mero is computed for each class at runtime and can be inspected using the dot underscore underscore amro attribute or the built-in Mero method. This sequence determines the path Python follows to find a method or attribute, moving from the derived class to each base class in the order specified by mro. For instance, if class C inherits from classes A and B, the model defines whether Python checks A or B first when searching for a method in C. This order is especially useful when classes share attributes or methods, as Mero ensures that Python uses the correct version without ambiguity. Understanding MO is essential in complex inheritance scenarios to ensure classes behave as expected. By following the C3 linearization, Python maintains predictable, deterministic attribute access across the class hierarchy, helping avoid the confusion and conflicts that can arise in multiple inheritance structures. Practical example. In this example, the D class demonstrates how Python's method resolution order malware works. Especially in the context of multiple inheritance, we have four classes A, B, C, and D. Class B and C inherit from A, while D inherits from both B and C. Each class except D defines a process method, which prints a unique message indicating the class in which it's defined. When we instantiate D and call D.process, Python needs to determine which process method to execute, given that both B and C have process methods that override A. Python resolves this by following the Maro, which is based on the C3 linearization algorithm. We can view the Maro for D using either D.__Maro or D.Maro, which both output the sequence D, B, C, A object. This sequence means that when Python looks for process in D, it first checks D itself, then B, followed by C, and finally A if necessary. As a result, when we call D.process, Python finds the process method in B first, so it outputs process in B. This NO sequence is crucial as it allows Python to consistently and predictably locate methods in complex inheritance structures. The C3 linearization ensures that Python respects both the inheritance hierarchy and the method resolution order of parent classes, avoiding ambiguity or unexpected behavior. This example highlights how Maro enables Python to handle multiple inheritance scenarios in a structured and reliable manner. Question 42. What is monkey patching in Python? Monkey patching in Python is the technique of modifying or extending existing classes or modules at runtime, typically by adding, altering, or overriding attributes, methods, or functions. This approach allows developers to change the behavior of code without altering the original source files, which can be particularly useful when working with third-party libraries where direct modification may not be possible. For instance, if a third-party class lacks a needed method, a monkey patch can add that method dynamically to fulfill specific project requirements. The flexibility of monkey patching can be powerful for quick fixes, prototyping, or adapting code to meet immediate needs. However, this technique should be used with caution as it can make code difficult to understand, maintain, and debug. Since monkey patches modify classes or functions in unexpected ways, they can introduce side effects that affect other parts of the codebase, potentially leading to bugs or conflicts, especially in collaborative projects. Practical example. In this example, we use monkey patching to modify the behavior of the greet method in the person class. Initially, the person class has a greet method that returns the string hello. When we create an instance of person and call person.greet, it outputs the original message. To demonstrate monkey patching, we define a new function new underscore greet, which also takes self as a parameter, allowing it to be used as an instance method and returns the modified string hello patched world. We then apply the monkey patch by reassigning person.greet to our new underscore greet function, effectively replacing the original greet method in all person instances. After applying this patch, calling person.greet now outputs the updated message hello patched world, reflecting the modified behavior. This example illustrates how monkey patching can dynamically alter the behavior of existing classes or modules without changing the original source code. While monkey patching can be a quick way to customize behavior or fix issues temporarily, it's important to use it judiciously as it can make code less predictable and harder to maintain, especially in larger code bases or collaborative projects. Question 43. How do you create and work with context managers? In Python, context managers are a convenient way to manage resources, ensuring they are properly acquired and released, even if an error occurs during execution. Commonly used for handling resources like file operations, database connections, and network connections, context managers help avoid issues like resource leaks by guaranteeing cleanup actions. This is especially valuable in scenarios where resources need to be released immediately after use, regardless of whether the code executes successfully or raises an exception. Context managers are typically used with the with statement, which provides a clear and concise syntax for resource management. When using the with statement, Python first calls the underscore underscore enter method of the context manager to acquire the resource, then executes the block of code within the with statement. Upon exiting the block, Python automatically calls the underscore underscore exit method, handling resource cleanup or release even if an error occurs within the block. You can create custom context managers by defining a class with the underscore underscore enter and underscore underscore exit methods. Alternatively, Python's context-lib library offers a context manager decorator, which simplifies the creation of context managers by allowing you to use a generator function to yield the resource and then handle cleanup after the yield statement. Context managers improve code readability, make resource management safer, and help ensure robust, predictable behavior when working with resources that need to be carefully controlled. Practical example. In this example, the file manager class demonstrates how to create a custom context manager for handling file operations. By defining underscore underscore enter and underscore underscore exit methods, file manager ensures that a file is opened and closed properly, even if an exception occurs within the with block. This approach enhances code safety and simplifies resource management, especially for operations that require careful handling like file I/O. The underscore underscore enter method in file manager is responsible for opening the specified file with the given mode such as read or write and returning the file object, allowing it to be assigned to the variable in the with statement file. In this case, the underscore underscore exit method handles cleanup by closing the file automatically once the code block under the with statement completes, ensuring that the file is closed regardless of whether the block exits normally or raises an exception. Using this custom context manager, we can write to a file by opening it in write mode W and then reading the content back by opening it in read mode R. When writing, file manager opens sample.txt and writes hello world into it. The file is automatically closed once the with block exits. When reading, the content is retrieved and printed, and the file is closed immediately after reading. This example highlights how custom context managers like File Manager allow for efficient error-safe file handling, encapsulating resource management within the class and keeping code clean and readable. Question 44. What is the difference between overloading and overriding in Python? In object-oriented programming, overloading and overriding are techniques used to define methods that share the same name but serve different purposes. Here's a breakdown of each aspect of these concepts and how they apply in Python. Definition: overloading allows multiple methods to have the same name but with different arguments, enabling a single method to perform different actions depending on the input parameters. In contrast, overriding is when a subclass redefines a method that exists in the parent class. Overriding allows the subclass to change the behavior of the method, creating a specialized version tailored to the subclass's needs. The purpose of overloading is to give flexibility to a single method so it can handle varying types or numbers of arguments, making it versatile for different scenarios. Overriding, on the other hand, enables a subclass to modify or extend the behavior of an inherited method, often to fit more specific requirements or to refine the parent class's general behavior. Support in Python. Python does not support true method overloading as found in other languages like Java or C, where you can define multiple methods with the same name but different signatures. Instead, Python achieves similar functionality by using default arguments, variable length arguments, args, quads, quad type checks within the method to handle different cases. In contrast, Python fully supports method overriding. When a method in a subclass has the same name as a method in the parent class, Python automatically uses the subclass's version, allowing subclasses to provide specific implementations for inherited methods. Practical example. In this example, the calculator and scientific calculator classes illustrate the concepts of overloading like behavior and method overriding in Python. The calculator class has an add method which uses default values for the parameters y and z. This approach allows add to handle one, two, or three arguments, achieving a form of overloading without needing multiple method definitions. For instance, calling calc.add5 returns 5, calc.add5 10 returns 15, and calc.add5 10 15 returns 30. This flexibility is achieved through default arguments which simulate overloading by allowing the same method to handle varying numbers of inputs. The scientific calculator class, which inherits from calculator, overrides the add method to introduce additional functionality. In this subclass, the add method has an extra parameter CRT, which is set to false by default. When CRT true, the method calculates the sum of the inputs by calling the parent class's add method using super and then returns the square root of the result. For example, psi underscore calc.add5, circa true returns the square root of 5, approximately 2.236, while psi underscore calc.add5, 10 15 security true returns the square root of 30, approximately 5.477. If security is not specified or set to false, the overridden method simply returns the regular sum. This example shows how default arguments can be used in place of true overloading in Python, allowing a single method to handle multiple argument configurations. It also demonstrates how overriding enables a subclass to extend or modify the behavior of an inherited method, adding new capabilities while retaining the core functionality of the original. By combining these techniques, we can design methods that are both flexible and extendable, enhancing the functionality of the base class without altering its original structure. Question 45. What is strong typing in Python? In Python, strong typing refers to the language's strict enforcement of data types, meaning that objects retain their types during operations and incompatible types cannot be used together without explicit conversion. Unlike some languages that perform implicit type conversions, Python requires that types are explicitly compatible for any operation. For example, attempting to add an integer to a string without converting one of the values would result in a type error, because Python does not assume how the data should be converted. This strong typing system ensures that Python treats data types consistently, helping to catch errors early by enforcing clear and predictable rules around type usage. Each object in Python has a specific type that determines the operations it supports, and this type is checked at runtime to ensure compatibility. While Python is dynamically typed, meaning variables do not meet declared types when they are created, its strong typing ensures that once a type is assigned, it is respected during operations. For instance, adding two integers is valid, but adding an integer to a list without conversion would raise an error. Practical example. Example. In this example, we see Python's strong typing in action. Here we define two variables, number and integer with the value 10, and text string with the value hello. We then attempt to add these two variables using the operator. However, because number is an integer and text is a string, Python raises a type error as it does not allow implicit type conversion between incompatible types. Python's strong typing requires that both operands are of compatible types for operations like addition, so adding an integer directly to a string is not permitted. To handle this, we use a try except block to catch the type error and print a message indicating the nature of the error unsupported operand type S for int and str. This strict type enforcement helps prevent unintended behavior as it forces developers to ensure that operations are logically correct. If the intent were to combine these values as text, we would need to convert number to a string explicitly using star number before concatenation. This example illustrates how strong typing in Python requires explicit type compatibility, adding a layer of safety by preventing unexpected type interactions. Question 46. What is the purpose of the global and non-local keywords? The global and non-local keywords in Python are essential for managing variable scope, enabling access and modification of variables in outer scopes from within a function. These keywords help control the visibility and mutability of variables across different levels of nested functions, allowing you to influence variables outside the immediate local scope. The global keyword is used to declare that a variable is defined at the global level, making it possible to modify a global variable from within a function. Without the global keyword, any assignment to a variable within a function is considered local by default, and Python will not modify the global variable, leading to a new local variable with the same name instead. By declaring global variable underscore name, you signal to Python that the variable should be referenced from the global scope, allowing you to change its value directly from within the function. The non-local keyword, on the other hand, is used in nested functions to access variables from the nearest enclosing non-global scope. This is particularly useful in scenarios involving nested functions where you want to modify a variable defined in an outer but non-global scope. By using non-local, you ensure that the variable from the nearest enclosing scope is accessed and modified rather than creating a new local variable within the inner function. This approach maintains the variable state across function calls and facilitates controlled access to outer scope variables, promoting efficient nested function behavior. Practical example. In this example, we demonstrate the use of the global and non-local keywords to modify variables in different scopes within nested functions. We begin by defining total underscore count as a global variable initialized to 0. This variable is accessible throughout the entire script. Inside the outer function, we define a local variable count, also initialized to 0. The outer function then contains an inner function, inner, where we use global and non-local keywords to modify variables from the outer scopes. Within inner, the global keyword is used with total underscore count, indicating that we want to access and modify the global variable total underscore count rather than creating a new local variable. This allows us to increment total underscore count by 1 within inner, reflecting the change globally. The non-local keyword is applied to count, which specifies that count refers to the variable defined in the nearest enclosing scope, namely the outer function. Using non-local, we can increment count within inner, and this change is preserved when inner exits. When inner is called within outer, it increments both total underscore count and count. The updated values are displayed within inner, showing count as 1 and total underscore count as 1. After inner completes, we print count from outer, confirming that the non-local update to count persists outside inner. Finally, when outer completes, we print total underscore count from the global scope, which also reflects the increment applied in inner. This example illustrates how global and non-local enable targeted modifications of variables in broader scopes. Global allows access to truly global variables from within any function, while non-local is used to modify variables in an outer, non-global scope, offering flexibility in variable management across nested functions. Question 47. Explain the concept of data descriptors in Python. In Python, descriptors are objects that enable customized behavior for attribute access within a class. They allow you to control how specific attributes are retrieved, set, or deleted, making them particularly useful for implementing features like computer properties, manage attributes, or attributes with validation logic. Descriptors follow a special protocol where a class implements one or more of the underscore underscore get underscore underscore set and underscore underscore delete methods, defining how attribute access should be handled. Descriptors are categorized into two types: data descriptors and non-data descriptors. A data descriptor is a descriptor class that implements both the underscore underscore get and underscore underscore set methods and optionally underscore undelete. Because it has a underscore underscore set method, a data descriptor is given higher priority in attribute lookups, meaning Python will use the descriptor's behavior whenever the attribute is accessed or modified. This is useful for cases where you want strong control over the attribute's value, as the descriptor can intercept all get and set operations on the attribute. For instance, in a managed attribute that requires validation, a data descriptor can be used to enforce rules each time a value is set. The underscore underscore get method handles what happens when the attribute is accessed. Underscore underscore set manages the behavior during assignment, and underscore underscore delete can define cleanup or deletion behavior. This protocol provides a high degree of flexibility, allowing attributes to act more like computed properties with automatic validation or transformation applied on access or assignment. Practical example. In this example, we use a data descriptor to control how the attribute of my class is accessed and modified. The data descriptor class implements the descriptor protocol by defining underscore 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 ret and underscore underscore set methods. Since it includes both methods, it is considered a data descriptor and has priority in managing attribute access and assignment for attribute in my class. The underscore underscore get method is called when the attribute is accessed, e.g. obj.attribute. It checks if the instance obj has an underscore value attribute. If underscore value exists, it returns its value, otherwise it returns no value set, indicating that the attribute has not yet been assigned. The underscore underscore set method is called when attribute is assigned a value, e.g. obj.attribute 10. It verifies that the provided value is a positive integer, setting underscore value on the instance if the condition is met. If the value is not a positive integer, it raises a value error, enforcing the constraint that only positive integers can be assigned to attribute. This validation provides an extra layer of data integrity by ensuring only valid data is stored in underscore value. When we assign 10 to obj.attribute, the underscore underscore set method sets underscore value to 10 on the instance. Accessing obj.attribute then triggers underscore underscore get, which retrieves and returns the stored value, resulting in an output of 10. Attempting to assign -5 to obj.attribute raises a value error with the message value must be a positive integer, illustrating how the descriptor enforces validation. This example shows the power of data descriptors in Python as they allow fine-grained control over attribute behavior, including access restrictions, validation, and custom responses for uninitialized attributes. This approach is commonly used to manage attributes that require validation, transformation, or specific behavior on access, making data descriptors a versatile tool for creating robust and managed class attributes. Question 48. How would you create an immutable class in Python? To create an immutable class in Python, we design the class so that its instances cannot be modified after they are created. This means that once the object is initialized, its attributes remain constant and cannot be changed. An immutable class is particularly useful in scenarios where data integrity, consistency, and predictability are essential, such as in multi-threaded applications where mutable shared data could lead to predictable behavior, or when dealing with fixed, constant data that should not change throughout the program's runtime. One way to create an immutable class is by using the underscore underscore setat method to prevent modifications after the object is initialized. By overriding underscore underscore setat to raise an exception if any attribute is reassigned after creation, we can ensure that the object state remains constant. Another common approach is to use property decorators with read-only attributes, allowing attributes to be accessed but not set. Additionally, underscore underscore slots can be used to restrict dynamic attribute creation, further enforcing immutability. Practical example. In this example, the immutable point class demonstrates how to create an immutable class in Python, where once an instance is initialized, its attributes cannot be modified or deleted. In the constructor underscore underscore init, we set the x and y attributes directly using super underscore underscore setitem. This approach bypasses the custom underscore underscore setat method to allow the initial values to be assigned, ensuring that the object can be initialized correctly without triggering the immutability enforcement. To prevent any modifications to the attributes after initialization, we override the underscore underscore setter method to raise an attribute error whenever an attempt is made to change the value of an attribute. This prevents the instance attributes from being reassigned, effectively making the object immutable. Additionally, we override the underscore 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 delete method to raise an attribute error if there is an attempt to delete an attribute, ensuring that the instance state remains fully intact. When we create an instance of immutable point with x1 and y2, we can access point.x and point.y as expected, and they output 1 and 2 respectively. However, when attempting to modify point.x by setting it to 3, the underscore underscore setat method raises an attribute error with the message stating that immutable point is immutable and cannot be modified. This approach effectively prevents any post-initialization changes to the instance, achieving true immutability for the immutable point class. This pattern is valuable for scenarios where data consistency is critical, as it ensures that the object state remains constant and cannot be altered after creation. Question 49. Explain the term method chaining and how you would implement it in a class. Method chaining is a programming technique in which multiple method calls are linked together in a single line of code, enabling a more fluent and concise syntax. This is particularly useful in object-oriented programming when working with classes that have several configurable or chainable methods, as it allows each method to be called sequentially without needing to repeatedly reference the object. Method chaining enhances readability by reducing the need for intermediate variables and making the intended operations on an object more visually clear. To implement method chaining in a class, each method should perform its designated operation and then return the object itself, typically using return self. By returning self, each method call returns the original object, allowing the next method to be called directly on it. For example, in a class that represents a data processing pipeline, methods like filter, transform, and aggregate could each perform a specific operation and then return self, allowing a single line of code to apply all three operations sequentially. Practical example. In this example, the query builder class demonstrates the concept of method chaining by allowing multiple methods to be called in sequence to construct a SQL query. Each method in the class returns the object itself self, enabling a chain of calls on the same instance without having to repeatedly reference it. This makes the code more concise and readable, particularly when constructing complex queries with multiple conditions and options. The query builder class has several methods to configure different parts of a SQL query. The table method sets the table name for the query, while the select method specifies which columns to retrieve. The where method allows one or more conditions to be added, each time appending a new condition to the underscore conditions list. The limit method adds a limit clause to restrict the number of results returned. Each of these methods returns self, allowing the next method to be called directly on the object in a single line of code. The build method then assembles the final query by combining the selected columns, table name, conditions, and limit into a complete SQL statement. This statement is returned as a string, ready for execution or further use. For example, calling query builder table employees.select id name position.where age 30 where position manager limit 10 build generates the SQL query select id name position from employees where age 30 and position manager limit 10. Method chaining in query builder enhances readability and efficiency, allowing each part of the query to be built in an intuitive step-by-step manner. This technique is especially beneficial for constructing customizable pipelines, configurations, or query builders where multiple settings or operations need to be applied in sequence. Question 50. How would you design a class to prevent it from being subclassed? In Python, you can design a class to prevent subclassing by using the special method underscore undate underscore subclass. This method is automatically called whenever an attempt is made to create a subclass, allowing you to enforce restrictions on inheritance. By overriding underscore underscore init underscore subclass in the base class and raising an error within it, you can effectively block any attempt to extend the class. For example, if you raise a type error or runtime error in underscore underscore init underscore subclass, any class that tries to inherit from the base class will encounter an exception, signaling that subclassing is not permitted. This approach is especially useful in cases where you want to protect the integrity of a class by ensuring that its implementation remains fixed and cannot be altered by derived classes. Classes that represent fundamental configurations, strict business rules, or single instance designs might be candidates for this restriction to maintain control over their behavior and prevent unintended modifications through inheritance. Practical example. In this example, the non-inheritable class is designed to prevent subclassing by overriding the special method underscore underscore init underscore subclass. When a class defines underscore underscore init underscore subclass, Python automatically calls this method each time a new subclass is created, providing a control point to enforce specific subclassing rules. Here, underscore underscore init underscore subclass raises a type error with a custom message whenever an attempt is made to inherit from non-inheritable class. This approach effectively prevents subclassing, as any attempt to create a derived class such as subclass will immediately raise an error. This restriction is enforced consistently, ensuring that non-inheritable class cannot be extended by other classes, which might otherwise alter its intended functionality or compromise its integrity. In practice, this technique is useful for designing classes that should maintain a fixed, controlled implementation, especially when the class represents core functionality that should remain unmodified. In this example, if someone tries to subclass non-inheritable class, the error message subclassing of non-inheritable class is not allowed is displayed, providing a clear indication of the restriction. By raising an exception in underscore underscore init underscore subclass, non-inheritable class enforces its non-inheritable nature while giving immediate feedback, making it clear to developers that subclassing is not part of the class's intended usage. Thank you for watching. We hope this deep dive into the top 50 object oriented programming questions in Python has been helpful in your interview preparation. Remember, understanding these concepts is crucial not just for interviews, but also for becoming a proficient Python developer. If you found this video useful, please give it a thumbs up, subscribe for more programming content, and don't hesitate to leave your questions or topics you'd like us to cover in the comments below. Good luck with your interviews and keep coding.